All right, thanks. Yeah, so I'm going to be here talking about Flock, which is a new fast snark. This is joint work with my advisor Benedikt, as well as Ron Rothblum from Succinct. Okay, so just to recap, snark is a cryptographic system that lets a prover convince a verifier that some computation was done correctly. And the key efficiency property of a snark is that for the verifier, this process must be much cheaper than actually doing the computation itself. So in particular, we want the snark proof to be short, and we want the verifier to be fast, much faster than redoing the computation. Okay, and such a primitive has many applications, both in blockchain and otherwise. I'll talk more about this later. For now, I just want to say that the starting premise of this talk is that in the real world, the key bottleneck of a snark's efficiency is the prover. So just to give a data point, this is from an A16Z blog post. The state-of-the-art ZK VMs, you can think of these as snarks for general-purpose machine computations, are many orders of magnitude slower than native execution. So in other words, if I take a program and I run it on my computer today, and then I also want to prove its execution, then the act of proving this takes, let's say, 100,000 times longer than doing the execution itself, modulo parallelization. Okay, and so the question that we're trying to study in this work is that, in a concrete sense, what is the smallest possible overhead that proving can have over native computation? In particular, we're going to be studying this for Boolean computations. So you can think of as a program as a circuit, a Boolean circuit, and we want to prove some evaluation of the Boolean circuit. This has been studied before, both in terms of theory as well as actual real-world systems, perhaps most notably the Binius snark. Okay, so there are two reasons why we care a lot about Boolean computations. The first is that they very naturally express cryptographic primitives like hash functions, which tend to dominate real-world snark workloads. And again, I'll talk more about this later. The other, perhaps more general reason is that they are a good proxy for measuring the actual cost of a native computation. In other words, if you have an application and someone optimizes the application to run faster on a real-world computer, then chances are that it's also going to correspond to, let's say, a smaller Boolean circuit and therefore get faster. And therefore, a snark for Boolean computations would then run faster on the same workload. Okay. And this is not the case for arithmetic computations necessarily. And a lot of snarks typically focus on proving arithmetic computations just because this is more natural for snark. Okay, so the main observation that we make is that in the real world, almost every single deployed snark workload that we care about it's not like an arbitrary Boolean circuit, but rather some more structured Boolean circuit. In particular, we're going to refer to this kind of Boolean circuit as like a batch computation. So you can imagine it's a circuit which has this sort of repeated structure inside of it, call it F, and for the most part, the circuit is basically responsible for computing F a bunch of times, as well as some logic sort of linking these values together. And so typically, you can think of like a classic example would be F is like a hash function. And if you're trying to prove, for example, like a hash chain or like a Merkle path opening, the vast majority of the circuit's work is just computing this hash function. And there's also just some like auxiliary logic linking these values together. And the same is the case for other applications such as signature aggregation and recursive proving. Okay, and so the main reason why we're interested in targeting batch computation specifically is that sort of by focusing our approach, we can try to get much faster proving than what we know how to do for arbitrary circuits. Great, so Flock is evaluated on the specific task of cryptographic hashing. Specifically, let's say you have a workload that sort of involves a ton of repeated hashes. How fast can we do it? And we benchmark Flock against this task. There are two reasons why we care about cryptographic hashes. The first is that they're sort of used everywhere. A lot of cryptographic primitives use hashing inside. And the second reason is that for snarks, they've been notoriously expensive to prove. In fact, so expensive that people have designed specific hash functions which are solely interesting because they're efficient to prove inside of snarks. So typically, this is achieved by constructing hash functions with more algebraic structure. Okay. So in this work, we don't want to use snark-friendly hashes. We want to target actual standardized hashes that are already used in the real world. And so we identified perhaps 3 of the most common hash functions being used, Ketchak or SHA-3, SHA-256, as well as Blake-3. Okay. And there are many reasons to prefer standard hashes over snark-friendly hashes. Their security is a lot more well understood. Snark-friendly hashes tend to have less scrutiny and cryptanalysis behind them. And in recent years, there have been many attacks reducing their security by exploiting their algebraic structure. Another reason is that standard hashes are extremely fast to compute. They've been designed to be fast on actual computers, whereas snark-friendly hashes are a lot slower to compute. Okay, so it might be the case that switching to snark-friendly hashes overall in your system is prohibitively expensive because they're just not fast on computers themselves. Okay, and so ideally, if we could use standard hashes, we would. And the goal of this work is to show that actually we don't have to resort to snark-friendly hashes. Standard hashes we can prove efficiently already. Okay. Okay, so that brings us to Flock. It's a snark for batch Boolean circuits. In terms of what the protocol actually looks like, it's fairly standard components, just with a ton of optimization thrown at it, as well as an extremely optimized implementation. And the headline number that I sort of want to report is that if you want to prove a bunch of hashes, then we can get a sort of prover time overhead of around 250x. Okay, and this is measured on a single core of an M4 max. So in other words, take the amount of time it takes to prove this batch of hashes, divided by the number of times the amount of time that it takes to actually execute these hashes, and the number is around 250 for the different hashes that we are benchmarking. I should also say there's like a very big caveat, which is that this is a proof of concept. This number is basically derived from the specific task of just proving a bunch of hash functions. So in reality, for a batch computation, there's also this additional logic outside of the hash functions themselves, and we're not benchmarking this. So currently we have simple examples such as like proving a hash chain or proving a Merkle tree Merkle path opening. But in reality, sort of this, I think one way to interpret this 250 number is that this is sort of this feasibility number. We're saying, okay, we can do the most expensive task, which is proving hashes at around 250x overhead, and assuming this sort of dominates your proving workload, you know, the actual overhead should theoretically converge towards this 250x number. Okay. Great. So I want to now explain what this like 250x overhead means concretely. And so throughout this talk, I'm going to stick to this specific application, which is signature aggregation. So let's say I'm a blockchain. Ideally, I want to be able to scale my throughput to, let's say, thousands of transactions per second. And also, perhaps more increasingly critical, I also want to switch to post-quantum signatures. So these are 2 potential goals that I might have as a blockchain. The issue is that both of them lead to significantly increased on-chain costs. So if I want to support thousands of transactions per second, then I'm also going to need to process thousands of signatures per second. And if I want to use post-quantum signatures, each signature is actually like an order of magnitude larger than what they currently are. So you can think of like post-quantum signatures as having sizes around like, let's say, kilobytes, whereas the current signatures that are being used today on blockchains like Ethereum and Bitcoin are all less than like 100 bytes. So both of these goals are in tension with on reducing on-chain costs, and also together they sort of magnify even further. Okay, so one proposal to support scaling to many transactions and supporting larger signatures is this idea of signature aggregation. Okay, and roughly the idea is that let's say I have a bunch of people that all with our own transactions, and we publish signatures. So instead of having all of these signatures on chain, I'm going to use a snark and prove that all of these signatures are correct. And this snark proof essentially acts as a signature for all of the transactions that I care about. Okay, and this gets published on chain. Okay, and let's get even more concrete. So recently there was this hash-based signature scheme that was proposed, and it uses around 160 hashes in its verification algorithm. Okay, so it's been optimized to reduce the cost of verification. And I want to imagine what a post-quantum blockchain would look like. So Ethereum in particular is strongly interested in using hash-based signatures for its post-quantum transition. And so one question I want to ask, and we'll answer later in the talk, is what is the maximum number of signatures that we can aggregate per second using a system like Flock? For Bitcoin, it's a lot less clear what they want to do, but most likely if they were to switch to a sort of post-quantum design, it would be using hash-based signatures, and in particular with SHA-256, because they already use it in their cryptographic stack today. And here, the concrete question I want to ask is, how long would it take to aggregate 5,000 signatures? Where this number 5,000 comes from sort of the number of transactions that Bitcoin processes in a block today. Okay. And importantly, like our snark proof needs to be small enough such that aggregation is worth it. So the aggregated proof should be shorter than all of these signatures like concatenated together. Okay, so let's get a Flock's numbers. So here I basically have Flock's throughput. So that's hashes proven per second for all of the hashes that we benchmark. So for example, single-threaded, we can prove around 80,000 Blake 3 hashes per second. And this represents a 224x overhead over the native computation of Blake 3 hashes. Okay, multi-threaded, and by multi-threaded, I mean on an M4 Max, so this is 10 performance cores. We can get around 660,000 Blake 3 hashes per second, and this represents like an 8x speed up. Okay, all the proof sizes are not extremely small, fairly small for hash-based snarks, and they verify in like a few milliseconds. Okay. So I also want to compare again sort of prior state of the art for each individual hash function. So for Keccak, Flock is around 4 times faster than Hashcaster, which is the prior state of the art in terms of its multi-threaded performance, 7 times faster than Binius, and 40 times faster than Plonky 3. For SHA-256, we're around 9 times faster than Binius. And for Blake 3, we're around like 14 times faster than Binius and Plonky 3. Okay. So returning to this example of signature aggregation, what does it look like? Well, if we instantiate the hash-based signature with our fastest hash function, which is Blake 3, we can prove around 660,000 Blake 3s per second. So this corresponds to being able to prove the hashing for roughly 4,000 signatures per second. Okay, so well above, like, let's say 1,000 transactions per second. For Bitcoin, if we instantiate Flock with SHA-256, we can prove around 330,000 SHA-256 per second, and this means that it would take around 2.5 seconds to prove the hashing for 5,000 signatures. Okay, again, this is with the caveat that right now we're only counting the time for proving hashes. So obviously when you verify signatures, there's also additional logic that comes with signature verification that we're not accounting for right now. But in principle, the hash cost is what's dominating, and so we would expect similar numbers for the overall, like an end-to-end aggregate signature implementation. Okay. So just some more numbers. In terms of proof size and verification, we instantiate Flock in like 3 different profiles. The first optimizes for throughput. The second optimizes for proof size and verifier time. And then we also have a variant which targets like a higher level of security. So 120 bits of security, whereas everything else on this table is targeting out like roughly 100 bits of security. And as you can see, for like our fast and slim profiles, Flock actually leads on all 3 axes simultaneously. So not just prover throughput, but also proof size and verifier time. Okay, so for the rest of this talk, I want to give a very high-level description of the protocol. So the actual protocol itself is fairly simple. It's sort of like this based on Spartan, which is this polynomial IOP. And I want to illustrate basically the 5 main steps of the protocol. So the first is that the prover needs to generate the witness itself. Call this witness Z. You can think of this as sort of all of the values in the Boolean circuit. And the prover is then going to commit to this extension, this multilinear extension of Z using a polynomial commitment scheme. Okay, so once Z is committed, I'm just going to define A, B, and C to be these sort of matrix vector multiplications of Z, where the matrices are derived from the description of the circuit. And we say that Z is a valid witness if A times B is equal to C, component-wise. Okay, so Flock then basically runs this zero-check protocol, which converts this input claim into multilinear evaluation claims on A, B, and C. Then we run this so-called lin-check protocol, which converts these evaluation claims on A, B, and C into an evaluation claim on Z. And then we run the polynomial commitment schemes opening in order to prove this evaluation claim. Okay, so this is a fairly standard protocol. And in terms of what we do, we basically just throw optimizations at essentially every step of the process. So there's probably too many to talk about. So I want to focus on one of them, which is this, how we leverage batch computations. I think this is probably where we get the most efficiency gains, actually, just from this step alone. It essentially reduces our lin-check cost from, let's say, like 25% of the overall prover cost to maybe like 5 to 10%. Okay. So the idea in lin-check is basically to reduce an evaluation claim of A to an evaluation claim of Z by representing an evaluation of A as some sort of sum-check claim. And this work of proving the sum-check is proportional to the size of this matrix A, roughly speaking. And so one of the observations that we make is that in this sort of batch computation setting where we're interested in just proving a bunch of repeated executions of a function, this matrix A actually has a very special structure. It's essentially, intuitively, it's like it's block diagonal. It's just this matrix A0 repeated a bunch of times. And if A satisfies this structure, it turns out that we can represent its evaluation as much smaller sum-check, where the work of proving this sum-check is actually only proportional to the size of this A0 matrix instead of A itself. So if we think of proving a large batch of computations, like let's say 1,000 repetitions of A0, then this lower sum-check is much, much cheaper than this original sum-check. And this is sort of how we make lin-check very cheap. Okay, so I want to end with some discussion of future directions. I think there's a lot of improvement for Flock. Again, it's a proof of concept. There's a lot more work to be done. I think we also live in we're in a time where a lot of these improvements are fairly easy to iterate on and test. So I'd encourage everyone to check it out for yourselves. So the first, I think, category of improvements I would consider is sort of end-to-end implementations. So for example, can we build sort of a general purpose VKVM using the same techniques as in Flock? So for example, you can imagine a machine architecture where we support like hashing instructions. And then when we prove the machine computation, we sort of take all of these hashing instructions together and then use something like Flock to prove them really quickly. I think also specialized applications are interesting as well. So we have some already sort of like hash chains and Merkle tree openings. I think it would be cool to explore other applications of interest, such as like recursive proving. Also this thing called like maliciously secured garbling, I think could benefit from something like Flock. In terms of performance improvements, we mainly focused on Apple Silicon as an architecture, just because it's easiest. You can obviously ask the question, on other architectures, what's the best we can do? So I have a number from Ron. Apparently he's gone like, on a 5090 GPU, like more than 10x faster than the multi-threaded numbers I reported in this talk. Another interesting thing is that you can also look at trying to just reduce the size of ththese hash functions themselves. So if we have SHA-256, we need to represent it as a circuit. The question is, how small can this circuit be? There's this like really cool website called ZK Golf that I'm sure many of you are aware of. It basically is this place where anyone can post solutions for like trying to minimize the circuit sizes of functions of interest. I think people have already like reduced, improved on sort of our constraints for things like SHA-256 and Blake 3. And so any sort of improvements here directly correspond to improvements to the performance of Flock. Okay, and then lastly, Flock is currently not zero knowledge. It shouldn't be too hard to add zero knowledge, but this is also open. Okay, and that's all I have. You can find our paper here, and as well as a proof of concept implementation over here. Thanks.
Actually, two questions. So first of all, is this easy to integrate into Jolt? That will be question number one. And the second question is, I didn't quite understand how this compares to Poseidon. So suppose you wanted to compare Flock on SHA-256, say batch, to Poseidon using Plonky 3, say batched. How do those compare?
Yeah, so I guess to answer your first question, I'm not so familiar with Jolt. Yeah, it's unclear to me. I would guess that it is. I don't know how their design works, but in principle, if I'm imagining like SHA-256 instruction in the ZKVM, it seems feasible to sort of try to isolate different like sort of the hashing work from the rest of the VM work, and then improve it individually, and then the VM would just be responsible for like connecting the inputs to where they are in the execution. Basically just imagining like all of your SHA-256 instructions as sort of no-ops when you prove the VM computation itself. Again, like I think there's probably a lot of work involved in actually doing like an end-to-end implementation, so I don't want to claim anything, but I do think it is possible. For your second question, yeah, I mean, in principle, like there's no reason these like arithmetic snarks can't take advantage of batching as well. A lot of our optimizations are building on things like Binius, and we are taking advantage of certain like architectural like aspects of like computer architecture which support like binary field arithmetic. So for example, we're using like AES and G, like we're using accelerated field arithmetic in some places to improve our numbers. So it's unclear what it would look like for like sort of arithmetic fields.
Okay, cool, thanks.
Yeah.
I have maybe, well, 1.5 questions. So your initial numbers about the native versus the proving time comparison, how large is the input size to your hash function, and how does it scale with the input size?
Which numbers are you talking about? Like the 250?
I guess the very initial ones, like the 650x, I believe.
Oh, I see. Yeah, so input size isn't really a factor. So we're imagining just the prover is committing to the trace, and then it needs to prove that these traces are internally consistent. In terms of like checking input consistency itself, I sort of glossed over this. This would be like a separate thing. So like if you imagine in a batch computation, right, so like some of these computations F, they're receiving inputs which are also just like intermediate values in a circuit. So you can think of like the verifier needing to test consistency, not just input-wise, but also like wire-wise, like intermediate wire-wise in the circuit. This is sort of not part of the accounting that we're doing here.
Okay, cool.
Cool. We have time for one more question. Yep.
So you're talking about aggregating hash-based signatures.
Mm-hmm.
How about, did you look into aggregating what's it called, lattice-based signatures, and what the impact on those would be? Because I think lattice-based signatures are also kind of candidates for post-quantum Bitcoin signatures.
Yeah, so to answer your question, we did not look at, or we did not try to imagine, like I don't have the numbers for like lattice-based signature aggregation. I guess the main thing is that if you wanted to like plug it directly into the code that we have, you would need to represent the sort of these lattice operations as Boolean circuits. It's unclear what the overhead looks like. So the reason why we are thinking about hash functions is that it's very clear what the circuit should look like for a hash function. It's less clear to me if like sort of Booleanizing a lattice-based signature verification is better than, for example, designing a snark which natively operates over the rings that like a lattice signature
you're talking about general purpose ZKVMs, so I imagine the application would be to do large spectrum of different computations.
Yeah, I mean, so right. So in principle, if you had like 1,000 or like 10,000 lattice signatures, then at some point, right, like the benefits you get from like thinking about it in this batch sense, like or maybe another way to say it is like the size of of a single verification circuit, even if you Booleanize it, is fine. It's sort of negligible compared to like the overall cost that you're trying to optimize. So in that sense, I would say yes.
Okay, well, thank you. Any Boolean computation, if you scroll to the slide where there's a batching of different functions illustrated, I guess every Boolean operation could be represented as XOR. So
every Boolean operation could be represented as XOR. You mean NAND or?
I mean, yeah, AND or negation or the OR operation. These are all representable as a XOR operator. So I guess all Boolean operations could be batched together.
Okay, yeah. So I mean, the point is that sort of the work. Like in order for this auxiliary logic G to be not the dominant cost, right? We want to represent this sort of batch computation in a way such that like most of the interesting stuff going on is in like, let's say at the F boxes. So if I view the F box as like a single NAND gate, then it doesn't really make sense. Yeah.
Awesome. Thank you so much. And we have a break.